one of the cooler things about quantum mechanics, and this is what makes this so fun, is that one of the easiest ways to understand it is to just go all the way back to the Big Bang. Now, just picture the Big Bang, like, you know when you have something that's like iron, like very dense, right? All right, well, let's just consider a singularity was smaller than a proton. All right, and it had a higher density than iron for sure. You know, probably a million times over or whatever. But the idea is that this thing swelled up. Nucleosynthesis took place. All right, and this is like the first formation of like the baryonic matter, like the proton. Okay, and these helium and lithium and hydrogen first form. Okay, and your space is still small, right? A fraction of seconds afterwards, you know. And over the years, as time went by, as it expanded, it cooled, and you had more room for electrons to like jump on to protons. You had atoms, and now light could move around. You know what I mean? And so space began to spread out, and it took a good while for it to get to where it's at now with the vacuum. Which, by the way, you know the CDM, the background radiation, right? That's completely harmless. You realize that that doesn't even hurt your body at all. Like, it's around you all the time, and it has no effect. It's a very old wavelength. Let's put it that way. You know, so very small wavelength and ineffectual in terms of the body. But about 400,000 years after the Big Bang, you had atoms, and eventually atoms clump up, you know, and so you got gases became stars, all right? And the first stars like lit up space with ionization, heavy ionization, like the kind you see when you're unprotected, when you're in orbit, let's say, where, you know, high-speed cosmic rays can come out of nowhere, protons flying at the speed of light, and they're extremely destructive. I mean, if they hit the upper atmosphere, they make pions and kaons, and they turn into muons, and then the muons come all the way down and, you know, pass through us. But there's like 10,000 muons going through your body or something like every minute. But yeah, these are the other particles. Like when particles collide and you get a reactive mass from that, that's what can happen. Like at the Large Hadron Collider, right? The LHC, what they do is they use a magnetic field to fire protons, and they do neutrons too. They do neutrons with iron, but they do them in groups. But the protons they fire, and they'll use a magnetic field to control it, and then they'll land it on something that's absolute zero and has a magnetic field controlling it as well. And what it does is it tells them it's a way to get a really energetic collision, you know. And so what they're always trying to do is prove whether this is a fluid dynamic vacuum state and something emergent, or is this, you know, in other words, like a particle's popping up because we're seeing the ripples, like dropping a rock in the water. You know, is this emergence or fundamental? So that's what physicists are constantly doing, is trying to develop ways of figuring out, is the electron fundamental? You know, is the photon fundamental? Is space-time fundamental? Or are these emergent properties? There's an argument in physics about time, and as to whether it is just a series of events, and therefore, in other words, if something's going to bump into something else, or something hot's going to deliver a heat load to something else, or electricity is going to move, or any vector of any gas or light or anything that moves. If it has to start at A and end up at B, it kind of needs time in order to do that. So like space kind of ends up needing time in order for causality to take place. You know, one chip behind the other, like in a chain. So it's to put it really simple, really far out away from our Earth, right? This is like 9 billion light years away. There's a galaxy cluster, right, called the Phoenix, and this thing is flying away at 400 million miles an hour. Now, so that means what people, when Einstein, you know, the lambda CDM, it's not a joke. It's actually, that's dark energy. That's what's driving the expansion. And so there's an energy value to the vacuum, okay? And as this energy expands, the quest was to try to find the driving force behind that. What is creating the displacement, or what is causing the energy? Because what happens is with a big mass, right, it will actually bend and warp the vacuum of space. So if you had an area that used to be a fluid, and you take matter away and take matter away and take matter away and take matter away, there's still a constituent like vector flow there. In other words, like you got a rock, you put it underwater, it gets submerged by the water from all directions. Well, space is doing that to the Earth and to big masses. It's submerging and bending its flows towards the mass. This Phoenix cluster has got like something like 2 quadrillion solar masses. It's a humongous gravitational basin, right? And the gravitomagnetic effects and tidal forces in this place, I can't imagine what it would be like, but this cluster of 2 quadrillion solar masses, trillions of stars, right, is leaving the big picture at 400 million miles an hour. It's just insane. The Milky Way is leaving this area, or you know, with this area, at like 1.3 million miles an hour. So like, you know, that's pretty dang fast, but nothing compared to the Phoenix cluster. I want to keep the videos short. My experience is in heating and cooling, and I understood vacuum state, fluids, pressures, temperature, things like that. So I had a background in science to a degree, a hands-on background to a degree. So that's why I was able to pick up some things in physics, and, you know, be able to relate them in a human way so that someone else can understand them. You know, because you might watch the show and like it, and it's great to you because I you know, the guy just like levels with you about different things in space that you might not know. You know what I mean? It's not like I'm saying like I have 5 doctoral degrees and every single thing I say is perfect. This is theoretical physics, so some of it is still up in the air. Like a physicist can tell you what's likely going on inside of a collapsed star, for instance, right? But they can't prove it. But they have the kind of spectroscopy that can pick up radiation in such a way, like, you know, when you go get an MRI done, right? You go get an MRI done, that's using quantum mechanics. They're actually using the spin of the atom there to use sound waves to take a picture. So like quantum mechanics is like, scientists have had their hands in this stuff for years. There's only a handful of places where it's really used now. One of them is in the photoelectric effect with solar panels. Another one would be quantum computing. Another one would be MRI machines. All right. Even phone companies use quantum entanglement to a degree, but quantum mechanics there's still a lot up for debate. There's still a lot more like room to grow. But anyway, that's today's show. I hope you like it. next week, the next one I'm going to do is going to be on, I want to get into Earth science, like the atmosphere, pressure, absolute pressure, specific gravity, why things go where they